Welcome to AI Frontiers, where cutting-edge artificial intelligence research meets real-world impact. Today we explore the robotics revolution, a collection of 17 groundbreaking papers from September 29, 2025, that showcase how machines are learning to dance through the complexities of our world. From aerial juggling to socially aware navigation, these AI-driven systems are mastering real-world complexity in ways that suggest September 2025 might be remembered as the month robotics truly came of age. Picture this scenario. A robot stands in your kitchen, watching you struggle with a stubborn pickle jar. Instead of simply demonstrating its superior grip strength, something remarkable happens. The robot observes your technique, understands your frustration, and gently takes the jar, not to show off, but to twist it just enough to break the seal before handing it back, preserving your sense of accomplishment and dignity. This isn't science fiction anymore. This nuanced, socially aware robotics represents the reality researchers achieved in September 2025, marking a fundamental shift in how intelligent machines understand and interact with human needs. Understanding why this research matters requires recognizing the massive transition occurring in robotics today. Robots are moving beyond factory floors into unpredictable environments, hospital corridors, busy city streets, and human homes. These new environments present exponential computational challenges. Modern robotic systems must handle incomplete information, adapt to unexpected situations, learn from limited examples, and interact safely with humans who may not understand their capabilities or limitations. The research examined today addresses these fundamental challenges through innovative approaches that combine traditional robotics with cutting-edge artificial intelligence techniques. Computer science robotics resembles teaching a brilliant but inexperienced alien to live among humans. This alien possesses incredible computational power and perfect memory, but must learn everything from scratch: how to see and understand the world, move through spaces designed for two-legged creatures, communicate with beings whose thoughts are expressed through language rather than code, and perhaps most challenging, predict human behavior in endless social situations. The field fundamentally differs from traditional robotics by embracing uncertainty, learning from experience, and adapting to new situations. It's the difference between a player piano that only plays pre-recorded songs and a jazz musician who improvises with any band, responding to crowd energy and fellow performers' creativity. The first major theme emerging from these papers involves hierarchical learning and policy decomposition. Think of this approach like teaching someone to cook a complex meal by first teaching individual techniques: how to dice onions, sear meat, make proper sauce, then showing how to combine these skills in different ways to create entirely new dishes. Multiple papers explore breaking down complex robotic tasks into manageable subtasks, enabling better generalization and interpretability. Peschel and colleagues introduce a framework leveraging vision language models to decompose task descriptions into executable subroutines, treating robotic APIs not just as execution interfaces, but as sources of structured supervision. This approach allows robots to understand and execute complex long-horizon tasks more effectively by learning modular skills that can be recombined in novel ways. The second theme centers on multi-modal perception and sensor fusion, where modern robots function like orchestra conductors who must simultaneously listen to dozens of different instruments and blend them into coherent musical experiences. These systems must integrate information from cameras, depth sensors, touch sensors, and other modalities to build comprehensive environmental understanding. Lee and colleagues present work on cooperative perception for autonomous vehicles, combining camera and other sensor modalities to enhance situational awareness beyond what any single vehicle could achieve alone. Similarly, Zhu and colleagues introduce APRIBot, which strategically combines LiDAR-based omnidirectional scanning with camera-based active focusing to achieve comprehensive environmental awareness for obstacle avoidance, demonstrating how strategic sensor fusion can overcome individual sensor limitations. Human-robot interaction and social awareness emerges as the third major theme. As robots increasingly operate in human environments, understanding social cues and human intentions becomes as crucial as understanding physics. This resembles the difference between a tourist who can navigate using a map but constantly violates local customs, and one who not only knows where to go, but understands how to behave appropriately in each cultural context. Nguyen and colleagues propose a framework for recognizing human group interactions using RGB cameras, enabling socially aware navigation that respects personal space and group dynamics. Tulbier and colleagues focus on task-oriented handovers, where robots must present objects in ways that support the human partner's intended use, integrating large language model reasoning with part segmentation to understand not just what to hand over, but how to hand it over appropriately. 5 revolutionary breakthroughs emerge from this collection of research, each pushing the boundaries of what's possible in robotics and artificial intelligence. First, the integration of large language models with robotic control systems enables robots to understand complex task descriptions in natural language and break them down into executable plans. Second, diffusion models achieve real-time robotic control, with Zhang and colleagues demonstrating unified pose estimation and control within a single framework. Third, cross-embodiment grasping works across different robot types, with Wu and colleagues creating the largest cross-embodiment grasp dataset, comprising 500,000 objects across 4 gripper types. Fourth, aerial juggling reaches superhuman performance, with Ji and colleagues achieving 462 consecutive hits. Fifth, cooperative perception creates collective robot awareness, where Li and colleagues enable real-time performance on mobile platforms, while significantly improving robustness under challenging conditions. Today's featured paper, Juggle RL, Mastering Ball Juggling with a Quadrature via Deep Reinforcement Learning by Ji and colleagues, represents far more than an impressive technological demonstration. This research tackles extraordinary challenges that push the boundaries of aerial robotics, predicting ball trajectories in real time, positioning accurately in 3-dimensional space while maintaining flight stability, executing precise contact maneuvers requiring split-second timing, and continuously adapting to changing ball dynamics. The system achieves an average of 311 hits over 10 consecutive trials in the real world, with a maximum of 462 hits observed. To put this in perspective, model-based baselines achieved at most 14 hits, with an average of just 3.1, illustrating the dramatic power of learning-based approaches for complex dynamic tasks. The engineering marvel behind Juggle RL addresses multiple sources of uncertainty through a comprehensive approach, combining large-scale simulation with systematic domain adaptation techniques. The system doesn't just learn to juggle in a perfect simulated world. It prepares for the messy realities where air currents affect trajectories, motor responses aren't perfectly predictable, and sensor measurements contain noise. The hierarchical control structure separates high-level decision-making from low-level stabilization, allowing the learned policy to focus on strategic juggling aspects while relying on proven control techniques for basic flight stability. Domain randomization during training exposes the system to balls with different weights, coefficients of restitution, and various starting conditions, helping the learned policy generalize beyond specific training conditions. This preparation proves crucial for the successful zero-shot transfer from simulation to real hardware. The implications of aerial juggling extend well beyond entertainment or demonstration purposes. The techniques developed apply to many contact-rich manipulation tasks that aerial robots might need to perform in the future. Construction robots positioning materials with precision, maintenance drones manipulating tools in confined spaces, and search and rescue robots interacting with debris and obstacles could all benefit from these advances. The successful zero-shot transfer from simulation to real hardware represents a significant achievement in reinforcement learning, demonstrating the maturity of simulation techniques and domain randomization approaches. Most importantly, this work shows that reinforcement learning has reached a sophistication level where it can tackle problems that seem almost impossible to solve through traditional engineering approaches, suggesting we're entering a new era where learning-based approaches can handle increasingly complex real-world challenges. Looking toward the future, the research landscape in computer science robotics resembles a river approaching rapids. The current is accelerating, new channels are opening, and the destination promises to be transformative. Several key directions are emerging that will likely define the next phase of robotics research. The integration of large language models with robotic systems points towards robots that can understand complex contextual instructions and engage in dialogue, asking clarifying questions and adapting based on feedback. Safety and robustness are becoming central concerns, with formal safety guarantees for learning-based systems crucial for deployment in safety-critical applications. Cross-embodiment approaches suggest universal principles of robotic intelligence that transcend specific hardware configurations. Cooperative robotics and swarm intelligence represent exciting frontiers where teams of robots accomplish tasks impossible for individual systems. The field is also moving towards sample-efficient learning approaches that acquire new capabilities with minimal training data. September 2025 represents a pivotal turning point in robotics history. We've witnessed the transition from rigid automation to adaptive intelligence, where robots demonstrate natural language understanding combined with physical capability. Social awareness has become as important as precision, marking the arrival of true human-robot collaboration. These breakthroughs showcase robots that can juggle balls in mid-air with superhuman precision, navigate complex environments using natural language instructions, and understand social cues in ways that seemed impossible just years ago. The research demonstrates that we've moved beyond the realm of science fiction into a reality where robots can truly live and work alongside humans. The next challenge involves scaling these breakthroughs globally, ensuring that the benefits of this robotics revolution reach communities worldwide while maintaining safety and ethical standards. This comprehensive analysis was created through AI synthesis, using Claude Sonnet 4, with text-to-speech generation via DeepGram technology, and visual content created with OpenAI image generation systems. The synthesized content underwent human expert review to ensure accuracy and clarity, though some oversights may exist in the complex technical material presented. All original research papers and their detailed methodologies are available through the archive preprint server for readers interested in deeper technical exploration. The synthesis process aims to make cutting-edge robotics research accessible to a broader audience, while maintaining scientific rigor and accuracy in the presentation of these groundbreaking advances in computer science robotics. Thank you for joining us on AI Frontiers, as we explored the remarkable robotics revolution of September 2025. These 17 groundbreaking papers demonstrate how machines are truly learning to dance through the complexities of our world, from aerial acrobatics to socially aware interactions. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archivepreprintserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archivepreprintserver.org.